Let's begin slowly and carefully. The claim that you may have already died in another universe sounds like science fiction. It sounds like late-night philosophy or internet mythology, but the roots of this idea do not come from fantasy. They come from physics, specifically from quantum mechanics, the most experimentally successful theory human beings have ever constructed. In the early 20th century, physicists were trying to understand something very small and very stubborn: atoms. Classical physics, the physics of Newton, worked beautifully for planets, cannonballs, and pendulums. But when scientists looked at tiny particles, the equations stopped behaving properly. Energy didn't seem continuous. Light didn't behave just like a wave or just like a particle. Something deeper was going on. Scientists like Max Planck discovered that energy comes in discrete packets, which we now call quanta. Later, thinkers such as Niels Bohr and Erwin Schrödinger developed a mathematical framework to describe how particles behave. And the strange thing was this: the math didn't describe solid objects moving along definite paths. It described waves of possibility. Imagine you throw a ball. In everyday life, you can calculate exactly where it will land. But in quantum mechanics, if you throw an electron, you don't get a single trajectory. Instead, you get a cloud of probabilities. The theory does not tell you where the electron is. It tells you the likelihood of finding it in different places. Here is where things become deeply unsettling. According to the equations, before you measure a particle, it does not have one definite state. It exists in what is called a superposition, a combination of multiple possible states at the same time. This is not poetic language. It is a precise mathematical statement. And when we perform experiments, the predictions match reality with extraordinary accuracy. To make this vivid, Schrödinger proposed a thought experiment. Imagine a sealed box containing a cat and a quantum device that has a 50% chance of releasing poison. If the quantum event occurs, the cat dies. If it does not, the cat lives. The mathematics of quantum mechanics says that until the box is opened and observed, the system evolves into a superposition of both outcomes. Cat alive and cat dead. That sounds absurd, yet the equations work. We have performed increasingly sophisticated experiments showing that tiny systems genuinely behave this way. Particles interfere with themselves as if they traveled multiple paths at once. Nature, at its smallest scale, does not commit to a single story until something forces a definite outcome. This is the foundation. Not speculation about parallel worlds. Not mystical thinking. Just the uncomfortable fact that at the deepest level we currently understand, reality is described not by certainties, but by overlapping possibilities. And once you accept that, the door to far stranger questions quietly opens. Now we come to the real tension inside quantum mechanics, the problem of measurement. The equations that describe quantum systems are clear and precise. They tell us how a system evolves over time. This evolution is smooth, continuous, and completely deterministic. If you know the wave function, the mathematical object that contains all the probabilities, you can calculate exactly how it changes. But when you perform a measurement, something strange happens. Suppose an electron is in a superposition of two positions. The wave function says it is both here and there, each with a certain probability. Yet when you measure it, you never observe a blur of both outcomes. You see the electron in one specific location, not both, just one. The mathematics that describes this jump from many possibilities to one actual result is not smooth. It is abrupt. Physicists historically describe this as the collapse of the wave function. Before measurement, multiple possibilities. After measurement, one definite outcome. But here's the problem. The collapse is not described by the same elegant equation that governs everything else. It is added almost as a rule. The theory tells us how probabilities evolve, but then it tells us that upon observation, one of them is randomly selected. What counts as a measurement? Does it require a conscious observer? Does it require a macroscopic object? Where exactly is the boundary between quantum fuzziness and classical definiteness? These questions are not philosophical decorations. They are central technical issues, and different physicists have proposed different answers. In 1957, a young physicist named Hugh Everett III suggested something radical. What if the wave function never collapses? What if the smooth equation always holds, without exception? If you take the mathematics seriously and refuse to insert a special collapse rule, then something extraordinary follows. When a measurement occurs, the measuring device becomes entangled with the quantum system. Instead of collapsing into one outcome, the combined system evolves into a superposition of outcomes. Imagine again the cat in the box. The quantum device becomes entangled with the poison mechanism. The poison mechanism becomes entangled with the cat. And when you open the box, you become entangled with the entire system. The result, according to Everett's interpretation, is not a single reality where the cat is either alive or dead. Instead, the universe splits into distinct branches. In one branch, you see a living cat. In another branch, you see a dead one. Both branches are equally real, but they no longer interact. This idea later became known as the many worlds interpretation. It sounds extravagant. Infinite universes multiplying at every quantum event. But from a certain point of view, it is mathematically conservative. It removes the mysterious collapse and simply trusts the equation. The key insight is that superposition does not disappear. It spreads. It includes the measuring device. It includes you. You do not stand outside the quantum system observing it. You are part of it. And once you accept that, measurement stops being a magical moment where possibilities shrink into one reality. Instead, it becomes a branching point where reality differentiates into multiple, non-communicating histories. This is not experimentally proven as the correct interpretation. But it is logically consistent with everything the equations say. And if it is correct, then every quantum event creates a branching structure of outcomes. That is where the idea of parallel universes begins, not from imagination, but from taking the mathematics at face value. If we take the many worlds interpretation seriously, then we must also take seriously its implications for macroscopic objects, including human beings. The mathematics does not draw a sharp boundary between atoms and cats, or between cats and people. If everything is made of quantum particles, and those particles obey the same equations, then in principle the branching structure applies to everything. Now we have to be careful. Quantum effects are usually tiny. In everyday life, objects appear solid and definite. You do not see chairs in two places at once. This is because of something called decoherence. When a quantum system interacts with its environment, air molecules, photons, surrounding matter, its delicate superpositions effectively spread out and become impossible to observe directly. The different branches stop interfering with each other. They become dynamically independent. This is important. Many worlds does not mean that you visibly split into two transparent copies. The branching happens at the level of the wave function, and decoherence ensures that the branches evolve separately. From inside one branch, everything looks classical and ordinary. Now imagine a scenario involving life and death. Suppose there is a device triggered by a quantum event, perhaps a radioactive decay with a 50% probability in a given time interval. If the decay occurs, it activates a lethal mechanism. If it does not, nothing happens. From the perspective of the wave function, both outcomes occur. The system evolves into a superposition of decay happened and decay did not happen. Through entanglement, this extends to the larger environment, including your body and brain. In one branch, the device activates and you die. In another branch, it does not activate and you continue living. Here is where the idea known as quantum immortality arises. The argument goes like this: you can only have subjective experiences in branches where you remain conscious. In branches where you die, there is no continuing experience from your point of view. Therefore, from your first-person perspective, you will always find yourself in branches where you survived. This does not mean you are physically indestructible. It means that among the set of all branches, the only ones you can experience are those compatible with continued awareness. Think of it like this. Imagine reality as a vast tree, constantly branching at every quantum event. Most branches are nearly identical, differing only in microscopic details. Occasionally, Some branches differ dramatically. If a branch ends your consciousness, there is no observer within that branch to register its continuation. From the inside, experience simply never reaches that endpoint. However, this reasoning quickly encounters serious difficulties. Probability amplitudes matter. Branches are not all equally weighted. If survival requires extremely unlikely sequences of events, the measure of those branches becomes vanishingly small. While they may exist mathematically, they may represent an infinitesimal portion of the total structure. Moreover, consciousness itself is poorly understood. We do not know what it means physically for awareness to follow one branch rather than another. The theory does not contain a built-in concept of a migrating self. It only describes evolving quantum states. So while it may be true that in some branches you have already died, and in others you continue, it is misleading to imagine a single you hopping between realities. The wave function contains many versions, each evolving according to the same underlying laws. From within any given branch, there is only one continuous narrative. The unsettling part is not immortality. It is multiplicity. If the interpretation is correct, then your existence is not a single line through time, but one strand in a constantly branching structure. And that forces us to reconsider what we mean when we say, I. Let's make this more concrete with a slower, more careful thought experiment. Imagine a machine connected to a perfectly isolated quantum system. Inside that system is a particle prepared in a superposition of two states. The machine is designed so that if the particle is measured in state A, nothing happens. If it is measured in state B, a loud click occurs. The probabilities are exactly 50-50. Before the measurement, the particle is not secretly in A or B. The mathematics describes it as a linear combination of both. When the machine interacts with it, the machine itself becomes entangled with the particle. The combined system evolves into a superposition, particle A with silent machine, and particle B with clicking machine. Now imagine that you are inside the room. When the measurement happens, you hear either silence or a click. According to the many worlds picture, what actually occurs is that the entanglement spreads to include you. There is now one branch where you heard silence, and another where you heard the click. Each version of you remembers a definite outcome. Neither version has access to the other. Notice something subtle. From inside either branch, it feels as though one random result occurred and the other possibility vanished. But from the standpoint of the full wave function, nothing vanished. The evolution was smooth and continuous. The apparent randomness arises because each observer becomes correlated with only one outcome. Now extend this setup further. Suppose the clicking outcome triggers something fatal. Silence means survival. The branching still occurs. In one branch you continue to observe. In the other branch, your brain ceases functioning. From the inside, what does this mean? In the branch where you survive, you remember hearing silence. In the branch where you die, there is no continuing memory, no further awareness. There is no perspective from which death is experienced as an ongoing state. Experience simply terminates. This leads to a peculiar asymmetry. You can experience survival repeatedly. You cannot experience non-existence. If branching happens many times, and some branches contain fatal outcomes, then subjectively you only ever find yourself in non-fatal branches. But here we must introduce an important concept, probability weight. In quantum mechanics, each branch has an amplitude. The square of that amplitude gives the probability associated with that outcome. When events are repeated, branches where unlikely outcomes occur repeatedly become extremely low in weight. Picture a tree where each split produces thick and thin branches. The thick ones represent high probability outcomes. The thin ones represent rare events. Over time, some branches become unimaginably thin. They still exist in the mathematical sense, but they represent an extremely small fraction of the total structure. If survival depends on a long chain of extraordinarily unlikely events, the branch supporting that survival becomes exceedingly thin. From a global perspective, almost all branches may contain death at some stage. Only a tiny subset continues. This challenges the intuitive version of quantum immortality. While it is true that experience can only occur where consciousness persists, it does not follow that survival remains typical or robust. The measure of surviving branches may shrink dramatically as conditions become more extreme. Another difficulty is that decoherence does not create perfectly clean splits. Branches can be enormously complex, involving astronomical numbers of interacting particles. The idea of neatly separable worlds is an approximation. The underlying reality is a single vast wave function with intricate structure. So the thought experiment teaches us something precise. If many worlds is correct, then life and death outcomes correspond to branching histories. From within any history, events appear singular and definite. From the outside mathematical description, they are components of a larger superposition. The unsettling implication is not that you cannot die. It is that the total description of reality may include both your death and your survival, embedded in different regions of the same evolving quantum state. At this point, it is essential to slow down and separate speculation from established science. The mathematics of quantum mechanics is extraordinarily successful. It predicts experimental results with astonishing precision, in some cases to more than 10 decimal places. Technologies like semiconductors, lasers, and MRI machines rely directly on quantum principles. So when we talk about superposition and entanglement, we are not dealing with fantasy. These are experimentally verified features of nature. However, the interpretation of what the mathematics means is another matter. The core equation of quantum mechanics, the Schrödinger equation, describes how the wave function evolves smoothly over time. That much is not controversial. What is controversial is how to understand the transition from a superposition of possibilities to the definite outcomes we observe. The many worlds interpretation is one way to resolve this tension. It removes the idea of wave function collapse entirely. Instead of saying that one possibility becomes real and the others vanish, it says all possibilities persist in separate, non-communicating branches. But this interpretation is not experimentally confirmed as uniquely correct. There are other interpretations that reproduce all known experimental results. For example, collapse theories propose that the wave function genuinely collapses due to some physical mechanism. Hidden variable theories, such as the pilot wave approach, suggest that particles have definite properties guided by a deeper deterministic structure. As of now, no experiment decisively distinguishes between these interpretations. They all agree on measurable predictions. They differ only in the underlying story they tell about reality. This is a crucial point. When people speak confidently about parallel universes as if they are established fact, they are stepping beyond what experimental evidence strictly demands. The many worlds interpretation is mathematically consistent and taken seriously by many physicists, but it is not universally accepted as the final word. Now consider the idea of quantum immortality. It is not a direct prediction of quantum mechanics. It is a speculative argument built on top of the many worlds framework, combined with assumptions about consciousness and subjective experience. We do not possess a complete scientific theory of consciousness. We do not fully understand how subjective awareness arises from physical processes in the brain. Without such a theory, claims about how consciousness behaves across quantum branches are necessarily tentative. Furthermore, probability in many worlds is subtle. If all outcomes occur, what does it mean to say one outcome is more probable than another? Physicists have developed arguments showing that the usual probability rule, the Born rule, can emerge from the structure of branching amplitudes. But the philosophical interpretation of probability in a deterministic multiverse remains debated. Another unresolved issue is the measure problem. In an endlessly branching universe, how do we define the relative amount of reality corresponding to different outcomes? Without a clear answer, statements about what you are likely to experience become conceptually delicate. So what do we actually know? We know the equations of quantum mechanics work. We know superposition and entanglement are real physical phenomena. We know decoherence explains why macroscopic objects appear classical. We do not know whether reality truly splits into many non-communicating worlds. We do not know how consciousness should be understood within quantum theory. We do not know whether the language of parallel universes corresponds to something physically fundamental or merely to a convenient mathematical description. The honest position is one of intellectual humility. The idea that you may have died in another branch of reality is a logical possibility within one interpretation. It is not an experimentally verified fact about the universe. And that distinction matters. The difficulty humans have in grasping the implications of the many. World's interpretation goes beyond mathematics. It is deeply psychological. Our brains evolved to navigate a single, continuous, and predictable environment. We interpret events as linear cause and effect sequences. We expect one reality, one timeline, and one version of ourselves progressing through it. This expectation shapes almost everything about how we think, remember, and make decisions. When confronted with the idea that every quantum event could produce multiple branches, each containing a version of ourselves, our intuitions break down. It is not that the mathematics is wrong. It is that our minds are not built to handle branching trees of existence. We struggle to imagine millions, billions, or even infinitely many copies of reality, each slightly or dramatically different. Our language and concepts, identity, self-continuity, are built for one path through time, not a fractal structure of possibilities. Probability, which we take for granted in everyday life, also becomes confusing. In ordinary terms, a 1% chance of an event seems rare. We can picture it happening once in 100 trials. But in a branching multiverse, every non-zero probability event happens somewhere. Tiny probabilities do not mean unlikely to occur. They mean occur in a relatively thin branch of the multiverse. Every outcome that can happen does happen in some branch. And yet, as observers, we experience only one branch at a time. This discrepancy between global occurrence and local experience is counterintuitive. The problem intensifies when we consider identity. We think of ourselves as singular. I am me, we say. But if the universe continuously branches, there are countless versions of you, each following slightly different paths. Some made different choices. Some experienced different outcomes. Some may even exist in extreme divergence where conditions are unrecognizable compared to the reality you know. Which one is really you? In one sense, all of them are. In another, none of them fully match the mental model of the self you inhabit at this moment. Identity, continuity, and individuality begin to dissolve under the implications of branching reality. This is why attempts to explain or visualize many worlds often fail. Popular metaphors, infinite Earths, parallel timelines, or other selves living alternate lives are crude approximations. They try to fit an enormously complex, high-dimensional mathematical structure into three-dimensional images our brains can comprehend. The danger is in mistaking the metaphor for reality. The branches of the universal wave function are not like separate planets floating in space. They are distinct components of a single evolving quantum state, entangled and interconnected in ways that defy ordinary spatial intuition. Even physicists struggle with this. It is not simply a matter of technical understanding, it is a matter of cognitive limitation. We can calculate probabilities, simulate quantum systems, and verify experimental results. We can accept the mathematics. But integrating the consequences into a coherent picture of existence, understanding what it means to be a person in a branching universe, is profoundly difficult. Ultimately, the struggle is rooted in perspective. From the inside of a single branch, reality appears classical, ordered, and definite. But from the outside, in the abstract, mathematical sense, reality is a vast, continually branching structure. Reconciling these two perspectives is what makes the idea of many worlds so conceptually unsettling. It forces us to question not only the nature of physical reality, but also the assumptions we make about experience, identity, and probability. In confronting these limits, we see why the idea of having already died in another universe is both logically consistent and profoundly disorienting. It is not an easy concept to hold in the mind because it challenges the foundations of the mental models we rely on to navigate the world. It requires recognizing that our intuition is a tool evolved for survival, not for understanding the full complexity of a multiverse. The concept of quantum immortality, while fascinating, encounters serious scientific and conceptual challenges that prevent it from being accepted as a reliable prediction. One of the first difficulties is the measure problem in many worlds. In this framework, each branch created by a quantum event has a probability amplitude which determines its weight in the overall wave function. Not all branches are equally significant. Some branches may represent extremely unlikely sequences of events, while others dominate the structure of the universal wave function. The subjective experience of a conscious observer is thought to correlate with higher weight branches, but this correlation is not fully understood. Survival along extremely improbable branches may exist mathematically, yet the likelihood of consistently following such paths decreases drastically as events compound over time. In other words, while a version of you might survive one improbable event, surviving thousands or millions in sequence becomes effectively negligible, even if it remains logically possible. A second challenge is the nature of consciousness itself. Modern neuroscience has made significant strides in describing the brain's activity and correlating neural patterns with subjective experience, but a complete theory of consciousness remains elusive. We do not yet know why, or how a particular pattern of neurons gives rise to awareness. Without a physical understanding of consciousness, it is speculative to claim that a conscious self follows branches of the wave function in any meaningful sense. Quantum mechanics describes probabilities of outcomes for physical systems, not the continuity of subjective experience. There is no empirical evidence that awareness itself behaves like a quantum system that tracks surviving branches. Third, there are physical constraints that even the most optimistic interpretations cannot overcome. Quantum branching cannot prevent natural limits imposed by entropy, energy depletion, or catastrophic cosmic events. Stars burn out, planetary systems change, and matter itself decays over unimaginably long timescales. Even if branches exist where a version of you survives small-scale accidents, the universe as a whole is not immortal. Survival is not guaranteed in the long run, and the scale of quantum effects diminishes relative to macroscopic processes. Branching does not override thermodynamic inevitabilities. Another complication comes from the interplay between decoherence and branching. Decoherence ensures that macroscopic superpositions effectively split into independent branches, but the process is not perfectly discrete or easily separable. Branches are enormously complex and entangled with the environment, creating a continuum of states rather than cleanly divided worlds. The picture of neat, parallel universes with clearly defined outcomes is a simplification for intuition. The reality is a single, high-dimensional wave function evolving continuously, with branching as a convenient but approximate way to describe emergent classical behavior. Finally, the probabilistic weighting of branches implies that surviving highly improbable sequences is not typical. While subjective experience only occurs in branches where consciousness persists, those branches may represent an extremely tiny fraction of all possibilities. Survival may feel continuous locally, but globally it is rare. The concept of quantum immortality exaggerates the extent to which first-person experience guarantees long-term survival. It assumes continuity without considering the diminishing measure of surviving branches over multiple low-probability events. Taken together, these challenges demonstrate that quantum immortality is at best a speculative extrapolation, not a verified consequence of quantum mechanics. It relies on unproven assumptions about consciousness, the interpretation of probability, and the structure of branching. It cannot be treated as evidence that any individual is effectively immortal, nor does it provide practical insight into life and death in our observable universe. The idea is intellectually provocative and internally consistent within many worlds, but it remains firmly in the realm of theoretical speculation rather than empirical certainty. If we accept the many worlds interpretation as a serious possibility, then the implication is that life and death events correspond to branching histories in the universal wave function. Every quantum event with multiple outcomes generates distinct branches, and those branches encompass not only physical states, but also, in principle, the states of complex systems such as human beings. Each version of reality evolves according to the deterministic equations of quantum mechanics, but the observer embedded within each branch perceives only one sequence of events. From the global perspective of the wave function, there is a vast superposition of outcomes, including versions in which an individual dies, versions in which they survive minor accidents, and versions in which they make different choices entirely. From the inside perspective of a single branch, experience is continuous and singular. You do not perceive the alternative versions of yourself that exist in other branches. Your subjective reality is constrained by the branch you inhabit, and any branch where consciousness ceases is, by definition, inaccessible to observation. This creates a striking asymmetry. While all possibilities may exist objectively in the wave function, experience can only occur in branches compatible with ongoing awareness. From this viewpoint, it may appear as though survival is continuous, because the branches in which consciousness terminates are never experienced. Yet this perspective can be misleading if taken too literally. Survival is not guaranteed in the sense that branches favor one version of life over another. The measure of a branch, determined by the squared amplitude of the wave function associated with that outcome, dictates its relative weight in the overall superposition. Branches corresponding to extremely unlikely survival sequences exist mathematically, but contribute minimally to the global structure. While a conscious observer cannot inhabit a branch in which they are dead, the probability that a single branch allows continued survival over long sequences of high-risk events may be vanishingly small. The idea of experiencing uninterrupted survival in all circumstances is therefore not supported by rigorous analysis. The persistence of consciousness is constrained by the statistical structure of the branching wave function. Another subtlety arises from the entanglement of branches with their environment. Realistic macroscopic systems are never isolated. Interactions with countless particles cause decoherence, which ensures that branches evolve independently and appear classical. This process creates an enormous, high-dimensional structure in which outcomes are distributed continuously rather than discretely. The notion of separate, neatly parallel universes is an approximation designed to make this structure intelligible. In reality, the branches of the universal wave function are highly intertwined, forming a complex landscape of possibilities where defining discrete outcomes becomes conceptually challenging. Even within this framework, physical constraints remain. Quantum branching does not negate entropy, the second law of thermodynamics, or large-scale cosmic processes. Stars will burn out, matter will decay, and environments will become inhospitable to life. While it is theoretically possible that some branches contain a surviving version of an individual, those branches are embedded in a universe that is itself transient. The equations allow many possibilities, but they do not provide immunity from universal limitations. Thus, if many worlds is correct, it is accurate to say that in some branches of reality, an individual has already died, while in others they continue to exist. These branches are equally real in the mathematical sense, but from the perspective of the conscious observer within a branch, only survival is experienced. This perspective highlights the distinction between objective existence in the wave function and subjective awareness within a single branch. It challenges the classical notion of a single continuous self, replacing it with a model in which identity is a localized pattern within a vastly branching quantum structure. Understanding this distinction is crucial to interpreting the implications of parallel histories without conflating speculation with empirical certainty. If we continue to follow the implications of the many worlds interpretation, the unsettling conclusion emerges that in some branches of the universal wave function, versions of ourselves have already died. These are not ghostly realms or spiritual planes. They are mathematically real components of the same quantum state that describes our universe. Each branch evolves according to the same deterministic equations, yet they are effectively isolated from one another due to decoherence. No signal or influence passes between branches once they have diverged, which means that while multiple versions of reality exist in parallel, each is self-contained. From the perspective of a conscious observer, only the branch in which they continue to exist is ever experienced, creating the illusion that survival is continuous. This realization challenges the conventional understanding of identity and selfhood. Humans tend to think of themselves as singular, continuous entities traveling along a linear timeline. In the branching universe, however, there is no single you. There are many versions, each following different paths through the superposition of possibilities. Some make slightly different choices. Some experience different circumstances. Some may cease to exist in certain branches. The unity of identity is replaced by a distributed pattern embedded in a high-dimensional quantum structure. Each version feels real and continuous from its own perspective, yet all are mathematically distinct. This forces a profound reconsideration of what it means to be an individual. Even though some branches contain death and cessation of consciousness, the first-person perspective is necessarily confined to branches in which the observer remains alive. There is a subtle selection effect at play. Conscious experience can only occur where awareness persists. This does not mean immortality. It simply means that we cannot experience non-existence. The illusion of continuous survival arises because the branches in which we die are inaccessible to perception. The physical processes continue in all branches, but subjective awareness can only inhabit certain paths. This distinction between the objective existence of branches and the subjective experience of a branch is crucial to understanding claims about survival and mortality in a multiverse context. However, this does not imply that survival is typical or guaranteed. Branches are weighted by the squared amplitudes of the wave function, which correspond to probabilities in the conventional sense. Extremely unlikely survival sequences exist mathematically, but their measure is vanishingly small. Over long sequences of events, the majority of branches will contain termination points where consciousness ceases. While a surviving version exists in some branches, it may represent only a tiny fraction of the total structure. The notion of continuous survival is therefore a local, observer-centric perspective, not a global feature of reality. The mathematics allows survival in principle, but it does not make it probable or robust over time. This perspective also emphasizes the distinction between macroscopic determinism and quantum possibility. While the universe appears classical and orderly at large scales, the underlying quantum state encompasses an immense superposition of histories. Life and death, choices and chance, all unfold as components of a vast branching structure. The first-person experience is a single thread woven through that structure, but the thread is not unique in the global picture. Recognizing this distinction requires separating subjective continuity from objective multiplicity, and it highlights the fundamental difference between our intuitions about life and the underlying mathematics of quantum reality. Ultimately, acknowledging that some versions of ourselves have already died in other branches forces a reconsideration of mortality, identity, and existence. It is not mystical, not metaphorical, it is a direct consequence of taking the mathematical framework of quantum mechanics seriously. The branches where we die are inaccessible, but they exist as real, objective components of the wave function. From the perspective of the conscious observer, survival is experienced locally, but globally, reality contains both existence and cessation, intertwined in a continuously branching quantum structure that defies classical intuition. This view challenges the notion of a singular, continuous self and invites a more nuanced understanding of what it means to exist in a probabilistic, high-dimensional universe.